Hi, Ella. How are you?
Hi, Samar. How are you doing?
Okay, thank you.
Okay, let me send a message to people. Then we're live. Always fun to tag everyone in the channel across 12 time zones.
That's difficult task, I would say.
How's the class going for you so far?
It's okay.
Hi, Dinesh.
Hi, Dinesh.
Hi, Ilya. Hi, Samarth. How are you guys?
I'm doing okay. How about you?
CNNs are actually a very cool thing to talk about since our homework involves CNNs.
I'll touch a little bit of it, what we have in the homework.
That's great. So hopefully it will be useful to people.
Yeah, I will not go much detail, but I think that's kind of a prerequisite for this paper, at least to have a good high-level understanding. Oh, nice. I like your background.
Thanks. Yeah, like
that's not the background the Zoom provides. It's actually his home, I think.
Yeah, it's in apartment. I was very lucky with the view. It's not as glamorous when you go outside, but yeah, the windows.
Your filters are well defined, Ilya. So give you that view. Okay, so let me know when we can start.
I think we have 6 people. I know a couple of people can't come today. They texted me privately, but they are going to be watching the recording. So like the total view count is non-trivial, and I think yeah, we can start. Oh, let's wait for Akil to connect. Hi, Akil, and hi everyone else.
Hey.
Hello everyone.
Hey. Okay, so yeah, if you can grant me permission to share the screen.
Oh yeah, of course. Okay, can you try now?
Yeah, perfect. Okay, so thanks everyone for joining. I hope, is it okay? We can start now?
I'm gonna mute myself.
Okay, perfect. So thanks everyone for joining today. What I'm going to talk is about this paper, which is around understanding the convolutional CNNs for text classification. There are 3 key keywords in this title, I would say. One is CNNs. So what I'll talk about today is a little bit about CNNs. Then the next is text classification. I believe every one of us know about what text classification means, so I'll not touch base on it. And the most important word is this understanding. So essentially what this paper talks about is what we call as explainability, and how the CNNs can be explained, or in terms of what they have learned and how they are predicting. So this paper talks about a few techniques, how that can be done, and that's what we'll discuss. So before I go into the details of the paper, any questions, or how much are people comfortable with the idea of CNNs? Maybe just a rough thing. Okay, not okay. Okay,
I still have a lot to learn about them.
Okay, then let me start with a little bit intro of CNN. So what you see in this picture is what we have in our homework 2, essentially. So So this is kind of a CNN architecture. But before I go there, I may want to look at. So every CNN consists of, any CNN architecture will consist of primarily three things. First is what we call as the CNN layer, or in essence, they are nothing but the filters. And so that's one part. The purpose of the filters is to identify some hidden patterns within the, let's say, image or text or any other time signal that you're using, and that's their job. Once the input goes through these filters, then there is something called a max pooling layer. Now there are different, or pooling layer. Max pooling is one kind of pooling. What the job of pooling layer is to, in a way, you can think of it like a switch. It kind of picks the most common pattern which is existing and suppresses all others which are not relevant for the final, let's say, classification task. So in case of let's say our CNN in let's say text classification, so how does it, these filters can be interpreted or are assumed to be looking like, you can think of like n-gram detectors. So their job is to break this word into the kind of n-gram you have, and the job of the max pooling layer is to pick which n-gram is most relevant for the classification task. So that's what essentially on a very high level the CNN architecture looks like. So any questions on this slide? I mean, I know I have rushed it through, but just to, because this is important, this picture, having this picture in mind is very important for this paper.
So I would just like to add here, correct me if I'm wrong. So this was one thing that I was confused. So it might help people. The layers and the channels are pretty confusing for me. So I would just like to add that since the input can have multiple dimensions, so a layer can also, I mean, the filter can also have that much channel depth as the input, and yet it can produce different channel depth. This is because think of like each filter as producing the output for a single channel. So if you have, let's say, 4 filters, so it's actually basically 4 channels, or you can say vice versa. So that's very important. I was confused, so maybe
you're right, Dinesh. So what you see here, so this is a kind of sentence. If you look at it from a word point of view, it is broken into the 6 or 7 tokens, and each of these square boxes that you see are kind of filters, or in more generic terms, these are channels. And each of them are like, in this example, I have taken as bigrams channels or bigram filters. So essentially, every one, like this, you can think of it like F1, F2, F3, F4. Each of these filters or channels will look into a bigram at a time. And then it will do a convolution operation and give it a score which comes into this block. Okay. And then this row wise max pool, what will do is it will pick the maximum, I mean, these are numbers in these cells. It will pick the maximum number and assign and just keep it on the side. So what every filter is doing is it is kind of trying to convolve, find n-grams, and then max pool picks the biggest, which is giving the highest score. So in a way, after max pool, if you see this sentence or this document or whatever you are inputting, text gets transformed into what is called a doc vector or a vector. So this is in a way a vector representation of your sentence. Okay. Good.
So sorry,
yeah.
so I have a question with the last slide. So you mentioned about like the 4-gram CIN filters, but why there's like a combination of 2 words in the inputs of each filter?
Because it's a bigram I have taken.
Oh, okay, I see. All right, thanks.
And it's a very good question. So I'll just push your question a little bit more, which is exactly what we have in our homework. So if you see, it's exactly the same representation what I was showing, but slightly tilted. But now what you see is there are 2 filters or 3. So one is a bigram filter. There's 2, 3, and 4. What you see. So one is a bigram filter set. Another is a trigram filter set, and other one is a 4-gram filter set. So this reddish, what you see, are similar outputs what we are having here from a bigram point of view. So filter, you do max pooling. So every filter that you apply is a vector. So this, what you see on the vertical side, is nothing but the horizontal side. Okay. So this vector, and then what you do is you do a max pool. Okay. And you get this final vector. So this bigram layer, trigram layer, and 4-gram layer, each of them, after doing a max pool, will give you these vectors.
Can I ask?
Yeah.
So can you explain dimensionality a little bit here? So the input here, this sort of white matrix, right? So that's a 7 by 5. We have 7 words.
Yeah.
It's 5 because each word embedding takes 5
dimensions. Yeah. Your word embedding size is 5 here. It could be 100, 200, whatever.
Okay, then the first bigram filter is 4 by 5. Again, 5. Can you explain the dimensions? Why is it 4 by 5?
So this picture is a little misleading in a way. It's a little confusing. So what I propose is, imagine there is a depth component here with every word, right? So let's say it's a 5 dimension. So in depth, in volume, you have W. How can I draw that? So shapes. Is there a volume? Yeah. So if you see, this could be my W1, right? It's a volume. And what you see in the depth are your embedding dimensions. Okay. And you can think of them as channels as well, if you want. And now what happens is we take this one filter and we convolve it, move it like this. So every operation that so if let's say there are 7 words, right? So since it's a 1D, I'll get these bigrams. That's the 7 bigrams or 6 bigrams that will come, right? So every filter is convolving, is kind of performing the convolution operation one step at a time on every bigram. So first time filter number 1 will go, it will see I and love together and kind of do the convolution operation and put it here. Then it will move one step. It will take love and this and then do the same thing. So in a way, it will try to break this sentence into bigrams and come up with scores. So that's how. So if you see now, the dimensions are reduced from, let's say this was 7 cross 100 to maybe this is what, 1 cross 6 cross 1 cross 6. Yes. Does that answer the question? Or?
Yeah, I think so. Can you pull up the other diagram once again?
Yeah. So this filter which is going, right, this filter which is moving around it, if you see, it will generate this kind of vector what we have generated here in the row. So, okay, and then we do max pooling and we get it here. So again, if you see here, sentence matrix 7x5, 3 region sizes, which are nothing but 3 types of filters, and 2 filters for each region they call. So essentially you have 6 filters in play. Then you do the convolution operation, you get this filter vector. And then based on this filter vector, you do a max pooling, and you get, for every filter, you get one number out. So,
wait, so at the top is the 4 gram and in the bottom is the 2
yes.
gram.
Yeah. Yeah.
Okay. I was looking at them in reverse.
Oh, the opposite way. Okay. My bad then. Yeah, you're right. Yes. So 2 gram, 3 gram, 4 gram. Yeah, my bad. I should have mentioned it. Okay. So if you look at our homework, that's what they are asking us to implement. So, and then, so after every 4 gram, 2 gram, 3 gram, 4 gram, what we get are these, after max pool, these vectors, right? So numbers, 1 for every filter, right? And then you stack them together. And you get this one big document representation from different perspectives. Now, I call it perspective because in one way, you're looking at the whole sentence 2 words at a time, 3 words at a time, 4 words at a time. So it's a perspective. And then you're taking all those perspectives, then you go into the final classification problem, and you give it to either to a fully connected layer or to the final output layer for decision making. Everybody okay with these pictures? These 2 pictures? Okay. So now with this, I'll go into the paper. So like I said before, the filters are primarily responsible for identifying the n-grams. They are in a way called n-gram detectors, right? And the global max pooling, so with the combination, I would say they are kind of patterns. And the n with max pool, essentially the CNN is trying to do is finding the most relevant n-grams for classification tasks. So the idea of this paper is to break apart these filters, the numbers that were there in the matrices, and see if we could make out some interpretation, explainability, as in which n-grams are responsible for what kind of, let's say if it's a sentiment classification of which n-grams are contributing to a positive sentiment and which n-grams are contributing to negative sentiments. So let's say if we build this kind of classifier and we are positioning it as a very good solution, then to explain to business, how would you do that? That's what this paper helps us. They talk about kind of 2 kinds of interpretability. One is model interpretability and prediction interpretability. By definition, the model interpretability aims, like it says, to provide an explanation about what the model has learned from the training data set. Essentially, what are your filters sensitive to? What is your max pool? What n-grams are you looking at? And by the way, the CNNs in text are like, you can think of it like a brute force thing. They are not linguistically looking for any linguistic patterns or anything. They are just breaking your sentence, trying out all the combinations based on your n-grams, and then looking out for which n-gram is most suitable for your task. So there's no linguistic. If somebody says, oh, there's no linguistic work here, it's just brute force. Okay, So model interpretability again is about learning what, understanding what your model has learned through the training process. And prediction interpretability is about, okay, what, when let's say we give it a new sentence for inference and we get a prediction positive sentiment, then explaining why did the model assign this sentence as a positive review or a negative review. So that's the part which is covered by prediction interpretability. Okay. So in essence, what these guys are saying is, in this work, we examine to attempt how CNNs process and then use it for more practical, improving the model, providing explanations. And the steps, what is explained here is exactly what I just showed you in the diagram. So I'll not go through these. I'll go right into the meat. So yeah. So if you see background of what this section is telling is about those operations, what we just discussed. Essentially, let's say you have an n-word input text, which is W1, we embed. So you do embed every word with a d-dimensional vector. So now every word is a d-dimensional vector, and you get a d cross n matrix. We pass it through this convolutional layer, which is nothing but a sliding window, and this is the window size. So in case of bigrams, it will be 2, trigrams, it will be 3. And as a result, we do convolution operation, which is nothing but a dot product between the two convolutional, filter vector and the region vector. You apply a ReLU and then finally a softmax. So this is how the architecture is. So essentially, they are just assuming that we are, let's say, in this kind of space, just one filter, let's say, or one filter bigram, and then you do the convolution operation, get the vector, and then max pool, and then finally your classification. Okay, so this is the setup for the architecture. So any questions?
Can I ask a question about, I think in the earlier page, it mentions that each filter specializes in a family of n-grams.
Yes.
And I don't know if this is going to come up later, but could you explain like how that is determined or achieved?
Yeah, it's a very good question, very relevant. So it will come in more detail in the later part of the paper, but to answer it on a short basis is, every filter when it is running, if you imagine, every filter, each of these filters, when they are running over the text, right? When they are scanning the text in pairs, let's say of 2 or 3, then what essentially they are trying to do is they are looking for an n-gram which is, let's say, most relevant for my sentiment classification. So for example, love, right? In this, if this filter number 1 is more towards identifying positive words, it could be, I mean, the model learns it, and it's like it will try to identify positive words in it. So through back propagation, it will specialize itself in let's say positive words. An analogy with the image world of CNN is like, you can think of this filter 1 like an edge detector, horizontal edge detector. So in text world, it could be, it will be like positive words. So that's how the n-gram detector thing comes into play.
Okay, got it. Thank you.
And we'll go into more detail. I mean, we'll literally rip this apart step by step. Okay, so with this, the next section is talking about essentially the data sets. So the authors have used 3 data sets for their work. Essentially, this is the sentence polarity coming from, I think, movie review. MR is the movie review data set. ELEC is the Amazon product review data set, and Yelp review data set polarity. So essentially, they have set up the experiment with different kinds of data sets so that they can consistently report the results, saying, yes, what they have found is not just working on one kind of data set, it is working on a variety of data sets. And for their purpose, for their purpose, for experiment for word embedding, they said they have used GloVe gigaword 5 embedding, and then exactly the same architecture of bigram, trigram, and 4-gram filters, and essentially 10 to 50 filters. And for training optimization, they have used Adam. So I think more or less the same architecture what we have for our homework too. Now comes the most interesting part of the paper. So now we have started with the things. So so assume that we got these data sets, we have trained this convolutional neural network model, and now each of these layers, each of these cells are filled with some numbers, right? So we'll get numbers after training for these cells. So what they say is, the first idea they come up with saying that informative, what they call as informative versus uninformative engram. So what they mean is, let's say the pooled vector, right? So this is our pooled vector. Okay. So consider the pooled vector P on which the classification is based, right? So this is the last vector after pooling on which we are doing classification. So each Pj, which is a ReLU, stems from a filter engram interaction and can be traced back to that triggered it. So essentially what they are saying is this particular number that comes here. So let's say I'm just making up numbers here, 2, 1, 3, 0.5, -1, and maybe 10 or 1 again, right? So this is the activation which has come, which means when I say activation, when you do this dot product of the filter over the region, you get this number out. And what max pool will do is it will put in 2 here, right? So in essence, if you see what max pool is doing is it is picking this engram as output, as a preferred thing, because it says this is the most relevant engram for this filter across all the other engrams that this guy has seen. Okay. So that's what this here it is mentioned that we can trace back the UI which triggered it. Essentially, we can trace back this max pool number to the engram which made it happen, or which came here. And then they are saying that if we do this process for each of the filters, then you get a bunch of numbers in every cell, right? Or in other words, we can say we get the engram which was triggered or activated as part of this max pooling operation. So we know, if we look at this doc vector, we know which engram is currently present in it for every filter, right? Any questions? Everybody okay? Okay. Okay. So, and this collection. So if we now start collecting these words, so let's say this is one set from filter 1 which came out, right? Let's say this was something which came out from filter 1. Maybe this came out from filter 2. Right? So that way we get a set. essentially we are getting a set of n-grams for each of these positions. So this movie, so at the end, if you look at this vector, this is nothing but a set of n-grams which made through that max pooling layer, and they call this set as SP. And since this final max pool vector goes into the decision making or the classification layer, what they are saying is n-grams which are not in SP do not influence the decision making. So essentially, the words which made through in the, or the n-grams which made through in the document vector, they are only responsible for decision making, which is done later for by the last layer. So like here, if you see only this, whatever vectors are in here, they are only responsible. The n-grams which are in this vector, they only contribute in the classification task. All other n-grams, they are just ignored. Okay.
I
Yeah.
think so. If I'm not, what I think what sort of feels very peculiar to me about this is that if you go back to your slide there, so sort of when we do the max pool, if we think about this through the lens of n-grams that don't make it into the max pool, don't contribute to the classifier decision.
Yeah.
The max pool value, each value in the max pooled vector is sort of it's used both to represent the importance of the n-gram and also to communicate the sentiment information. Does that make sense? And it's sort of the role of every entry in the doc vector is twofold. It both shows which n-gram is important for that filter and also shows the sentiment.
Yes. So exactly. So it's when during the training process, when the backprop happens, then there is a back propagation which comes from the training sentiment side. What essentially the classifier is saying, okay, out of all these let's say max pool numbers that I have seen or n-grams that I have seen, I think love this and I love are more important for positive sentiment. So you're right. Essentially, this entire setup, the max pool, is trying to push the important n-grams up or make them more visible to the classifier, and then pushing down the non-relevant n-grams. And we'll see that this insight will come in the paper as well. But you're right.
That's very interesting. Thanks.
Okay. Any other questions? Okay. So this essentially we got the idea of this set, right? The SP or the last max pool layer n-gram set. Now what they come up with, I mean, this is more how they are contrasting with the traditional thought idea and what they think, but the new idea or concept they bring in here is what they call as deliberate n-grams and accidental n-grams. So to Ilya's point, deliberate n-grams, the n-grams that make up in that SP vector or this vector set, those are called deliberate n-grams because they scored high by their filter, right? Because they may be informative, they are really informative. But if you think, what is max pool doing? Max pool is just picking the biggest number out of this row, right? Now, if the filter is a negative filter, let's imagine this is a negative filter which is capturing negative sentiment, then even then max pool will pull out something here, even though that will be a very small number, but it will pull out a number. So let's say this is more triggered towards it. If let's say this is like -1, -2, -1 again, -10, -5, -4. If you see, all of them are negative. I mean, I'm just making it up. They'll not be negative. They'll be very, or they will be negative maybe before the ReLU comes in. But if you see here, now the max pool has to pick a number from here in this list. And that will make its way here. So it will be like -1. Now, does this mean anything for a positive classification? No. So this n-gram and -1 corresponds to this movie n-gram. So this movie, the n-gram will make up, and they are calling these n-grams as accidental n-grams. So in essence, what they are saying is, whatever is your SP set, whatever is your activated relevant n-gram set that you get in the max pool, some of those n-grams will be informative or deliberate n-grams, which are relevant for classification tasks. And some may be accidental, just because the model didn't have a choice. It had to pick one, it picked. Maybe the classification layer will then suppress this down further. But from a lens point of view, if you just look SP, it can consist of two kind of n-grams, accidental and informative. So that's the main idea. It's accidental and informative n-gram. And then it's a very neat thing what they say. What they say is, now let's say if we say this filter is more tuned towards identifying positive sentiment, and this filter is more tuned towards identifying negative sentiment, right? So they will contribute numbers here. And what you do is you just pick a threshold to say, okay, anything for this filter, to call it up, anything above this threshold is what I call as relevant n-gram for this guy. And anything below the threshold will be non-relevant. So what they are saying is, we assume that there is a threshold for each filter where values above the threshold signal informative information regarding the classification, while values below the threshold are uninformative. So in a way, what they are saying is, because these guys are contributing towards decision making, if I have a threshold, let's say if I just pick filter 1 and said, this is the threshold for filter 1, anything above the threshold is relevant for filter 1. Any n-gram that I see, any n-gram, if it is above this threshold, then it's a relevant n-gram for filter 1, and it is contributing to the decision making task of classification. I mean, does it make sense?
Is this threshold learned?
No, this is not learned, but can be learned.
Okay.
So I'll come to that. Part. It's afterwards. But I just want to set it up, these numbers and pictures in your head, as in what we are trying to do. We are trying to interpret every filter value which is there in this matrix, every max pool value which is here in this vector, and see if we can make out something from it. Okay. Okay. So assume that now, because we have trained the model, right? So we'll have a weight vector, right? And so in the end, in the final classification layer, it's, let's say if we had 3-class classification, then this is more like your weight matrix, right? So it's W transpose X or W transpose P is your classifier, right? The last layer. In every network, there is a last layer. And if you take if you look at like a weight matrix, it will be a W transpose X. And then it goes through softmax, and then you get your class. So let's say if you have 3 classes, then the weight matrix will be like this. And since my max pool is which is nothing but your features, is 4-dimensional. So this is a 3x4 matrix, W matrix. Everybody with me? Okay. So let's say if we get a sentence, we get the max pool vector. This is the max pool vector of the sentence. It gets multiplied. We do a matrix multiplication with this vector, right? We get a score, we pass it through softmax, and then we get a class out of it. That's the regular forward function after it is trained. Any questions? Clear?
Wait, once again, so what are, I spaced out a little bit. So we formed the C2, C1, C1, C3 sequence, right? That makes sense. And then what do we do once again?
Yeah, so let me do this. Let me duplicate this slide. Yeah, so in this case, in a regular forward operation, right, what will we do? Let's remove all this. This is noise. So we get a sentence, right? We get a sentence. We give it to our model, the CNN model. And in the penultimate layer, what we get? We get after max pooling, we get a doc vector, right? We get a doc vector, and then we have this weight matrix. Let me also remove this just to avoid confusion. We multiply it with the weight matrix, right? We do a dot product in the last layer.
Okay, so that's a linear layer.
Yeah, that's the linear layer. And then we get the classification out, right? What class we belong to. So we get the class out. Let's say C1, right? So one sentence coming in goes in the fully connected layer we do. Now we know this doc vector consists of filter 1, 2, 3, and 4, right? Or the top n-gram contribution of every filter. And then we get the class out. So what they say in the paper is now we can use this idea, this trained weight metrics to identify and say that, hey, in general, the filter 1 is more biased or more tuned towards class 1 or class 2. So, and that's what this picture is about. So if you see, let me remove this guy. So this is my W matrix after training. And if I map it to the same argument before, this block is representing filter 1, right? W1 filter X1, W2, X2, W3, X3. That's how the linear thing is. And this is nothing but the position of filter 1, this guy. So when you multiply it with the vector, you are multiplying it. You're multiplying this guy with filter 1 vector, right? So this is filter 1 output. This is filter 2 output, filter 3 n-gram, and filter 4 n-gram, right? The top n-gram. So in a way, this is the weight of this filter. What is the contribution of this n-gram into the classification task associated with first class, right? So it's a linear classifier. If it was a binary classification, this is just a line separating class 1 and rest of the classes.
Oh, I guess, okay, so you have three classes in the output. What confuses me a little bit, so there are three classes in the output because you get a three-dimensional vector
Yeah,
after
yeah.
multiplication. Why are there 4 cells in the bottom? It's 4 blue cells. So
Yeah, that's because I'll tell what is these guys are, but from a setup point of view, from a last layer point of view, I mean, if you look at this picture only, right? So
Mhm.
this guy is this first is the linear classifier for class 1. These weights.
Yeah, that's right. Yeah.
This is for class 2. This is for class 3, right?
Mhm.
Now, we can also interpret it in a slightly different manner. Is for class 1. For class 1, how are each of the n-grams coming from the filters weighted?
Mhm.
Right? What is their contribution in decision making for class 1?
Yep.
Right? Similarly, what is the contribution of each of these weights for class 2, class 3, right? So in essence, this first, if you look at vertically, this first column is having weights which are contributing, which are coming from filter 1
Mhm.
feature, right? And this is coming from filter 2 feature, filter 3, and filter 4 feature. These weights, or these can be associated to those filters. So now if you take a max of this column, what it tells you is to which class filter 1 is more biased or looking tuned to. So what these blue cells are telling is nothing but a max. And my bad, I didn't put description here. But essentially what this blue cell is saying is, after you have trained the model, you see this W matrix. You find the max in this column, and you see to which class is every filter biased to, or what is the quality of the class of every filter.
That's actually pretty brilliant. I think it's really hard to explain because it's not really, you're not taking the value, you're just mapping to the index of the
Yes.
row for the column, which is like, but
Yeah. So if I put in, let's say, just random numbers here, like 0.3 is the weight, 0.6 and 0.1, then this filter, or this dimension of the weights, this is filter 1 contribution in class 1, filter 1 contribution in class 2, and filter 1 contribution in class 3, right? The n-gram coming from filter 1's its contribution. And if we take a max of all these 3, then we know that this is C2. So that it's filter 2 is very much biased towards C2. So what they say is, this is essentially what they're saying. For every filter, what you do is you identify to which class this filter is associated to. And then what you do after doing this exercise, you go back to your sentence corpus or your data set. So imagine our data set is having 5 sentences in it, 5 reviews, right? And for every review, this is the what you see in the orange is the true class, whether it's a positive review or negative review or neutral review. This is the true class. Now, what we do is you build this kind of a data wherein for every sentence, we get this p-value, right? Which is the SP vector. So let me say this is p vector, just to now. So for every filter, we get these p values coming from doc vector, right? And for every filter, we know what is the learned dominating class, C2. Okay. So what we do is we build this kind of a pair to say for sentence 1, whatever is the number, whatever is the max pool value which is coming here is this, and it's a 1 because my filter 1 class and the true class associated with this sentence are same. So essentially my filter 1, whatever n-gram came in my filter 1 max pool, it is kind of contributing in the right decision making process. So it's a 1. And then if you look at sentence 2, it's a 0 because it didn't contribute. Or it missed because the true class is C1. Filter 1 is more tuned towards C2. And similarly, you fill all this cells. And that's what this thing is saying here, is essentially you build this kind of a pair for so the superscript here is the, let's say, the data set item or the one sample, sentence 1, sentence 2, sentence 3, and the subscript is representing the filter. Filter 1, filter 2, filter 3, filter 4. And this is the Boolean decision operation, which is like whether C1 is equal to C2. I mean, whatever class that we predict, we associated our filter to, is it true with the sentence class? So if it's true, then it's a 1. If not, then it's a 0. Okay. And then what they say is, what you do is you take every filter value, like you take all these values and plot them in, let's say, if let's say these are numbers, right? Again, these are numbers. These P1s, these P's are nothing but numbers. And you can think of it as this is their class. There's a positive, excuse me, positive class or 0 negative class. When I say negative, it's whether it triggered or didn't trigger or contributed in the decision making, or was relevant for decision making or not relevant for decision making. So it will be like a scatter plot in a way, in one-dimensional scatter plot, right? There will be, these are numbers. I know it's little hard to put it in
Which axis is which?
This axis.
Sorry, I mean, are ones and zeros y's or x's?
Ones and zeros are your decision, or your you can think it like their label. It's whether it was correct or contributing to the classification or not, or identifying the true class or not.
Okay.
So it's like let me. So if, let's say, this is my x. Yeah.
You would have like graph for every filter.
I'm sorry.
So for every filter, we'll plot this graph.
Yes. So this will be for every filter. You're right. And now you can put in, imagine P, every P is an X, right? So we can put in some kind of a, let me put in a circle, right? So every P is a circle on this axis.
Okay.
And some are, yeah, sorry.
And then you just like kind of mark them with 1 or 0.
Yeah. So you color them with, let's say, blue and red. Okay. So now, in a way, you have all these P's here and some red, some blue kind of plots here, right? And now, interestingly, what we can do is we can come up with, to your question, Ilya, we can come up with a threshold, a very good threshold to say, what is the P value which separates blue from red, right? For this filter. So for every filter, we can come up with the P value, which is kind of separating this. In an ideal case, what we expect is the this kind of separation. You just get one line which is separating blue and red. But in real world, this will not happen. So this could happen. So in that case, but essentially the idea is to come up with a threshold which separates these blue points with the red points, essentially blue n-grams with red n-grams now, in that manner, in that language. And that's what your quality of the filter is. That's where you get the threshold. And now any n-grams, now you take any n-gram in your corpus and compute the p-value of that, because you can do that convolution operation. And if it is above the threshold of that filter, then it is contributing to that filter. It's part of that filter. It belongs to that filter.
So better way, I think, at least what I was thinking was, if it's above the threshold, then it belongs to that class. Otherwise, don't. I mean, we are just making ReLU type of statement.
Exactly. And
Yeah.
that's what, I mean, just jumping, this is what it is. So what they are suggesting is exactly, Dinesh, what you said, is once you identify these threshold in your network, instead of ReLU, use these thresholds and see how is the performance.
Wait, but you use that threshold to test the performance, but you don't do any more training, or do you?
No, you don't do any more training. Or even in the training process, if you redo the training instead and use this threshold instead of ReLU, then the expectation is, at least in terms of validation, the expectation is that your model performance should not go down.
Okay, that's pretty incredible. Okay.
So, I don't know, Samarth, whether it's mentioned in the paper or not, but I was thinking, if we do this, aren't we just cutting off the interaction with different n-grams? I was just thinking, like,
that interaction is already taken care by your filters.
but now they're contributing to just one class.
No, they are all contributing to decision-making process, but at the end of the day, they are tuned towards one class. In every filter, like an horizontal edge detector will always find horizontal edges in images.
So, yeah, so that's what I was thinking, like, if there is some sort of degree, like that threshold only might be difficult to find that threshold.
So
is it?
So that's what, how to find that threshold is what they came up with, this metric called purity. So what purity is, a very simple idea. What they say is, if you go to this this plot, right, and just randomly keep on slicing different places where you say, okay, this is where I want. So what is the purity of your threshold? So you say anything above this threshold is what I consider okay, right? And let's say there are 10 points in total in that above the threshold, right? So let's say the threshold was here. So in total, there are 6 points in this, right?
Yeah.
Or bad example, let me make it a little better. Yeah. So there are total 5 points, 5 points. Now, let's say this was the point where we decided on a threshold value. So if I take this threshold value, what will happen is I have 6 points above the threshold, or 5 points, 3 out of which are actually correct and 2 are wrong. So, or 3 of which are actually tuned towards my filter, where my filter was correct. So what is the purity of this threshold? The purity of this threshold is 3/5. Or you can think of it like 60%. So that way you keep on moving across this line, and you try to, what they come up with, a golden threshold, common threshold value of, or purity value of 0.75. They say the threshold where you find 0.75 purity or 75% purity, take that threshold.
So is purity a kind of like accuracy in some sense?
It's kind of an accuracy in some sense. You're right. Accuracy beyond the threshold value that you have taken. So if threshold is here, you count all the points above it, and then you look at the accuracy. So in order to come up with the threshold, right threshold, you do this kind of, this is one way to come up with the threshold value. You just try out different threshold values and look out for a value which gives you 75% accuracy or purity. Okay. And then quickly, what this, once you have identified this threshold, what Dinesh was saying, you can actually replace, let's say, go in your test data set of your trained model, replace the ReLU layer with this threshold layer and see how the performance is going. And this is what they found. This first graph is essentially doing exactly the same thing. So what they saw is as for the 0.75 purity in thresholds, the training loss kept down. So it was performing very well, and then it increased. And then similarly test, they found the same thing. So what this proved, what at least they say is what this proves is, okay, if I replace ReLU with my threshold, the thresholds that I have identified for every filter, they are kind of working perfectly fine. They are not reducing my model's performance. In fact, they say it increased a little bit. So, so now since you know the threshold and we know all these dots are nothing but n-grams, in a way, we know which n-grams are contributing to the decision-making process. For every filter. So whatever filter we have learned, in a way, we know what are the key n-grams which are responsible in that filter, or which are making up that filter or working with that filter. So now we know about that filter. Like in image detection, in image processing or CNNs or computer vision, when we look at the filters, we say, oh, this filter is horizontal edge detector. Filter 1 is horizontal edge detector. Filter 2 is vertical edge detector. Now we can put in similar kind of explanation for the text-based filters and say, filter 1 is related to these n-grams. Filter 2 is related to these n-grams. So that's the analogy.
Wait, sorry, clarifying question. Is the thing that we infer the fact that some filters are related to some n-grams, or that some filters are related to some output classes?
Both. So what we learned by doing that was the process, this thing, it was just part of the process. So we learned both these things.
Can you, okay, sorry, I see how we do the filter class mapping. I don't, it doesn't click for me how we see that a particular filter cares about current type of n-grams.
So this part is clear, right, Ilya?
Yeah.
So the question is how the filters come to n-grams, right?
Right. So I guess if you tell me an n-gram, and then I can do the math with it, then I will be able to tell you this filter pays attention to it.
Yes.
That one doesn't. But I don't see how you could like qualitatively describe that n-grams of such kind are used in this filter and these are not, before you actually see them.
Yeah. So very good question. I mean, I had a hard time understanding that myself. So though this paper was only 6 pages, it took me a very hard time to understand. But if you look at, we are okay with this part, right? With the threshold. So let's say if we have learned the thresholds, right? For every filter, we know a threshold, right? A threshold value, which says that if I take an n-gram and convolve it with the filter, I get a value. And if that value is above that threshold, it belongs to, that n-gram belongs to the filter. Right? We are good with that. Now, let's say if we had a big corpus, like if we take all the n-grams in our corpus and pass it through filter 1, say, then we'll get a collection of n-grams which are kind of belonging to filter 1, right? Which will all fall into filter 1. Correct? So let's say if there were 100 n-grams, maybe 20 n-grams are these blue points which are above the threshold that we know. So those 20 n-grams are what is being described by this filter, or are in a way what identifies this filter. So maybe I'll just jump the paper a little bit to answer your question, Ilya. So if you see this is what they go into further, but essentially, yeah. So this is what they see. So what they did is they took all the data set, they divided it, they took all, let's say, n-grams or trigrams, and then what they did is they came up with these slots. Every word, n-gram can be divided into n's, right? 1, 2, 3. They compute the score, and that's how you come up with it, is the previous process. But then what they do is they do clustering on it, and in a way, what you see, they find these two clusters in this example, and there's a very good pattern in it. The first pattern is in this cluster is determinate intensity adverb positive word. So this is what one kind of pattern which filter 1 has identified, or filter 0, whatever filter has identified. That's one pattern. And the other pattern is the go wrong pattern. So this filter, we can, if we see go wrong, some trigram starting with go wrong, we can say yes, it will be part of filter 1.
Thanks. I have to drop for another meeting, but
yeah. So I think if we are already over the time, so I'm sorry I couldn't finish this, but I think the rest of the paper is built on the same idea. So I don't know if anybody else wants to, if people are okay continuing, or we do it sometime later.
So I'm okay continuing. Like right now, it's really in the flow, so we can at least start.
Others?
Yeah. Also, I still need to learn about it for the assignment because I'm a little bit behind on schedule, so I want to learn as much as possible.
Okay, then let me continue for another 20 minutes because it might be late for others. But essentially, you got the idea, right? Or are there any other questions? Because this is important to understand. It's more of an explainability, like I was saying, but it's important to understand the threshold and how we got to the threshold. Is everyone okay? Then I can move forward. Okay. So now what we found as part of this process is which n-grams are contributing to which filters. Now the next question is, what Eli was saying is, what is actually captured in the filters? We know there are 100 n-grams that belong to filter 1, but is there still any other hidden pattern in those 100 grams that we can use to see what this filter is actually capturing? So to identify that, what these guys are coming up is the idea of what they call as slot activation vectors. So slot activation vector is nothing but essentially every n-gram, right? every n-gram is made of words, right? I and love. So bigram is made of 2 words. So what you do when we convolve, this weight will be a 2, let's say if the word vector was 100 dimensions, right? So this bigram filter will be of 2 cross 100 dimensions as well, because they do a dot product. So what they say essentially is count the dot product of every weight with love. So how to give an example is, okay, let me take this guy, right? Just as an example. So let's say this is your word vector. This is vertically word vector. And this is my, so in my bigram, I'll have 2 words, right? So this is word number 1. And this is word number 2. Right? And these are the dimensions, let's say. And what is convolution? Convolution is nothing but it does what convolution does it takes this guy and this guy, stack them up, and essentially take a random filter weights. So these are your filter weights, stack them up, and you do a dot product, and then you get a number out of it. You do a dot product between the 2 things and you get a number. That's what your convolution operation is doing.
So is each box represent a character?
No. It's a word. So this word I
Oh.
is 5-dimensional, right? So, or 4-dimensional. Every word is 4-dimensional, right? We gave a dimension. So every word is 4 dimensions. So these are, let me, so this is word 1. All the representation of word 1. This is word 2 of, oh, sorry. This is your word 2. What is this? And this is your filter. What you see in gray is your filter weights. And essentially convolution operation will just do a dot product between these 2 and come up with a number, right? A single number. It will be like a single number here, right? When you do a dot product, you get a single number out.
Okay, so each of the dimension is the output from the previous layers of filters.
Each output is an output of one convolution.
Okay.
So like here, when we are doing convolution, right? So we were convolving I love with a filter, and we got a number out here, right? This is the output of the convolution. Okay.
Okay.
So it's a number which comes out of a single number which comes out of the output of a convolution. And then you move the filter next, one more step, you get these 2, and you get another, you do another, again, the same convolution operation, you get a number out, a single number. So what these guys are saying is, okay, we get a single number. Until now, we have analyzed things like that. But what if we break this into individual numbers or individual words? So we can also look at it like this, that, okay, let me, we kind of get 2 numbers out. One number is, let's say, so this is word 1, right? I being represented and love being represented. And the final convolution operation we know is nothing but a sum of, we do a dot product, essentially multiply and sum it, right? This can also be seen as if I just multiply this guy with this guy and this guy with this guy, right? I can look it from this. I get these 2 numbers. If I sum them, I get the same number. So just a different way to look at the same operation. But what this does is you can see now, take this number and this number, which is nothing but your slot activation. So this is one slot of your filter and this is another slot. Or you can call it word activation of your n-gram filter. Okay. Any questions on this operation? Everybody okay with how we are looking at the convolution operation, breaking it into two slots of convolution? Okay, so essentially this is what is being explained here in this equation. So what you do is you take these and then, I'll just skim through quickly here. What you do is you can now, let's say, oops. Yeah, okay. So yeah, now what you can do is you can then look at every n-gram and break it into slots, right? Slot 1, poorly, the score dot product operation score is 5.47. Design dot product operation is 0.07, junk is 0.87. And if I sum them up, then I get 7.31, which is what we used to get as one full output of the convolution. Okay, so this is what I was explaining as in how the dot products and the breaking of slots work. Now what they say is they come up with the idea of what they call naturally occurring n-grams and possible n-grams. So essentially what they say is if I have a vocabulary of my data set or corpus, right? So looking at my corpus, I can get the complete vocabulary out of it. And then what I do is I can make combinations of two words from the vocabulary and then come up with all kind of possible n-grams. So possible n-grams are nothing but you take all the words of your vocabulary and just combine them in, let's say if you're doing bigrams, combinations of two. So those are all possible n-grams that you could come out from your vocabulary, right? Naturally, and as you can think of, sometimes those possible n-grams make sense. Like they'll make sense. Love this, love, act, love something. And so some of those possible n-grams will be nonsense. Some will be making sense. The ones that are making sense, which again you get from your corpus, they call it naturally occurring n-grams. They are natural n-grams. They are correct n-grams in a way. And naturally n-grams will always be a subset of possible n-grams. And then what they did is they found the, let's say for every filter, what they're saying is for every filter you find the top n-gram contributor. So I can take, like this is a trigram example. So I can go in my corpus and look for or apply my filter to all the naturally occurring trigrams and get a score out of it, right? So let's say I have a list of all naturally occurring trigrams. I apply my filter 0. I get a score out of it. I get a number out of it. And then I sort it in terms of descending order. So I pick, let's say, the biggest, the one trigram which is having the highest score. Let's say in this case, it was poorly designed junk. Right? And then look at the slot scores of each of that n-gram. And I do this for all the filters. Let's say there are 9 filters. And then at the same time, what I do is I take the same filter and run it through all the possible n-grams, all possible n-grams. And then I do the same sorting and get the topmost. So this is what will come. And the sum, okay? if you, what they observed, if you look this table, is there is a very hidden pattern in here. So one hidden pattern is that the regular or the non-natural engrams, they are always greater than the natural engrams. So there's some will in almost every case will be greater. Second, what they found is, if you look at each of these slot scores, they said not all slot scores fire, or they are not having, if you look at the weightage, 5.45, 0.97. So 5.45 is way bigger than 0.97 and 0.98, which means in this filter, poorly is contributing heavily compared to designed and junk. So what they found is essentially that if you look at the slots, not all slots are high values. Maybe there are only 1 or 2 values which are high compared to others. So for example, like this one, utterly useless. In this case, slot number 1, which is belonging to utterly, and slot number 2, which is belonging to useless, those two are contributing heavily to the overall score. So that way, what it is showing is that, hey, not all words. So from n-grams, now we can pinpoint to the words actually which are contributing more. Okay. And compared to randomly, this is what the normal thing comes out. And in this, if you see, what they are highlighting are the words in all possible n-grams. If you see the ones which are highlighted, like slot 3 is always, and these are top 7 words from, let's say, filter 0. And for it, you can see that slot 3 belongs to words like invaluable, perfect. Slot 2 belongs to words like holding, works. So that's what is being shown here. So essentially, now we are able to even figure out which words are contributing to which filter. That's the whole idea. Any questions with this?
I think I was just thinking like it's having a word which has more activation can. I think there is one more deduction that I made actually. That I was thinking that we can identify whether it's a useless. Useless. I think that's a wrong word, but I would say a non-natural and natural easily, because if the activations are high for each, then it might be that it's not naturally occurring.
Yeah.
So
that's
maybe that's also helpful in some way.
I would say maybe not, because it could not be a but part of what your inference, Dinesh, is correct, because if you read through the paper, they'll talk about like suppressing n-grams versus activated n-grams.
Yeah.
So they do talk about it, but not in terms of natural versus possible, but could be one interpretation. I have not thought it in that fashion, so I couldn't comment, but I think part of it, what you inferred, is correct. So they are highlighting the idea that the filters and the filters do, or max pooling do, get suppress few n-grams and activate or bring up the other words which are more important. So then what they did is, okay, they took it to the next level essentially. And I'm just quickly jumping it because we are already. So what they did is, they did a very peculiar kind of exercise wherein they just took these slot scores and did clustering. For every filter, they did clustering. And what they found is, in every filter, there are different kind of clusters which form. So essentially, like the one I was showing right here, they found that one cluster is for filter 0 is determinant, intensity, adverb, positive word. So now this is a great insight. You know about the filter. The filter is activated if it sees a determiner, intensity word, and a positive word. If it's a trigram filter, and if it sees this pattern, then this filter, it belongs to this filter.
So basically, by clustering, they're trying to identify which sort of n-grams the filter is identifying, because
Yes.
here we were just saying that it in a vague way. We were saying in a very vague way that these are the type of n-grams that belong to these class would be identified.
Yes. So it's another level. So first we said filter on a high level belongs to this class, but this filter itself is made up of different things. And one of the things is this kind of pattern.
So these determinant, intensity, adverb, these are the three parts of the trigram.
Yeah. The first one, second one, third one. First word, second word, third word. Okay. And if you see, and the second one, the pattern they found, they are referring here is go wrong. So anything starting with the first two words go wrong, it belongs to this filter. That's another kind of pattern which they found. So you can think of it like identifying topics also in other terms. It's like topics. So these are the topics going into one cluster. These are the topics going in another cluster. So a filter, for one filter, I can build this kind of insight for every, and I can do this for every filter. And I think that's it. I mean, these are just talking, though, taking the same ideas and talking in more detail about it. But the key takeaway is you identify what a filter is made up of. You identify what max pooling is doing. So essentially, the class identification part comes because of max pooling. This topical or semantic class identification of the filter comes from these slot activations. So yeah, so that's essentially what we have. So that's how the interpretability comes into play, or that's how they are bringing interpretability into the mix. Okay. So I think, I'm sorry I have to run through this and I was slow, but I think I covered the most important or the key concepts and ideas which were. You can ping me if you have more questions or something is not clear in this paper. I will be happy to answer to the best of my ability. But any questions, anything that you want to ask around this? We have 3 minutes. So
one short question. So before like feeding into the CNN filters, so does each word being processed and vectorized by some sort of like embeddings already?
Yeah.
Okay.
So if you see this thing, the assumption is that maybe you have generated word to vec or glove vectors for every word, and that's how you represent the word.
See. Okay.
Even one hot encoding is also okay. I mean, that's also simplest representation you can go with to start.
Let's see.
Any other questions? Okay. Anything?
No, I just would like to say thank you so much, and it was one of the most clearest, I would say.
Yeah, thank you very much, Samarth. It's very nicely explained. I have to go through again to understand a bit more, and I'll come back if I have any questions.
Sure. Anytime.
Thank
And
you.
my apologies. I couldn't.
No. Don't say that. You
constraint.
have spent a lot of time and you have explained it to us. So we are just thankful, you see.
Yeah, I learned a lot. Especially I haven't started my week 5 videos. So.
I think Jen, you are the most benefited person today, I think.
Yeah, I'm very grateful for this clear explanation.
No, I would say for homework too. I mean, I have done it. Because I have worked with this architecture, I know about it before, so it was easy for me. But for when I did it first time, when I was studying about it, it was one of the toughest ideas to wrap my head around. And this picture, actually, I found this I found in a different paper, but I thought this is a very good picture summarizing what you are going to do in homework too, at least in the CNN space. I thought maybe it's also easy for people if I share, they get this. Rather than going through the text, if you now go through the text, what the TAs have mentioned, you can relate it here with this picture.
You happen to have a link to that paper as well.
Yes, I do have. I can share it with you guys.
Thank you.
But that paper will not give you any information what you want in the homework. I just stole that picture because it was good. But I'll send out the picture. I mean, I'll send it to you.
So, just one question popping up in my head regarding that slide 4. Can you just move to that? I
Mhm.
think, yeah. So I was just thinking that the prediction, the gold standard, which is it the basically actually a human annotator, or is it the basically
This one,
yeah,
you mean to say this? So in
Yeah,
your
yeah.
data set, sorry, in your data set, you know these labels, right? So in your training data set or test data set, you already know these labels.
Yeah, so I was just curious, like this is really still very new to me. Like this filter is like I've been used to that the filter represents some feature of the data, that's fine. But the filter is also representing some sort of class. So in future, if I change the class, then filter is also going to change the class. That's going.
It's this is something what this paper is saying, that you can, there's a way to associate a class contribution to this filter, or you can
Yeah.
assign what and you don't change the classes after training. Like whatever class you have assigned to a sentence, you will not change it.
Mhm. Still, I mean, I just was thinking like, if there is a filter which has a highest weight, let's say 0.6, but there are some other filters who have some weights, maybe let's say 0. Maybe negative weights as well. I don't know.
Yeah,
So
yeah,
in
that's
that
fine.
case, the result would be skewed, and we won't be having the correct prediction. I mean,
So these weights, just to maybe interrupt, sorry, these weights are learned from your classification task. So the assumption here is you have done your classification, you have trained a classifier,
okay, yeah, I see.
and it is performing to your liking on your data set. Now what you want to open up your model to see how it has come to that conclusion what you are seeing. So it's like a anatomy of your model to interpret. So let's say if you go to your manager or someone for whom you are building this classification, you're selling it, and that person comes up and says, no, I don't believe you. How did this happen? How can you explain? What is this filter telling?
Okay.
So then you can say, or it gives a sentiment, gives you a review and says, your model says it's a positive review, and you are questioned, how can you say this is a positive review? How did the model know this is a positive review? So then you need that kind of explainability. You need those tools to explain what model learned. That's model interpretability and prediction interpretability coming into play. So this entire thing assumes you have a trained model.
Yeah, this is not going to help in training anyway, right? This is
Yeah.
just for interpretability.
Yes.
I see. Okay.
Okay.
Thank you. Yeah. Thanks so much. Thanks a lot.
No worries. Okay, then I think my Mac is also saying close it. I'll take leave, and thanks a lot, everyone, for your time and
Thank you very
patience.
much.
Really
Thank you.
appreciate. And Emily, I'll send out the link to you for that paper.
Okay, thank you.
Okay. Talk to you
Thanks.
guys.
Bye.
Bye bye.